All right, what about the corresponding statement of this? What's the integral statement of the above?
1 over x dx equals to ln of x plus c.
Okay. And that's something that you should be aware, because often people make the mistake of applying the wrong rule. So, if you want to integrate 1 over x squared, how would you do it? You rewrite this as x to the negative 2 dx, right? And you apply the power rule, which says you add 1 to the exponent and put the reciprocal in front, right?
So negative 2.
And plus c, right? Yeah, you add 1 first and then put the reciprocal.
Yeah, you're right, okay.
Yeah, and then that's negative 1 over x plus c. The problem with 1 over x is that if you try to do the same thing with the 1 over x and write it as x to the negative 1 dx, then you get x to the 0th power and the reciprocal will be 1 over 0. It doesn't make sense. Okay. In fact, what I failed to say last time is that the power rule, I don't want to write it again, but the power rule has an exception. You can't use the power rule if the value of n is negative 1. You can only use it if it's not negative 1. Yes?
I just have a question. So
yes.
Shouldn't the negative 2 go to the x and then it becomes minus plus 1, and then wouldn't it be negative 2x minus 1?
No, you might be confusing the integral and the differentiation.
Yeah.
The integral rule is you add 1 to the exponent and put the reciprocal in front.
Oh, okay. I see.
Always add 1 to the exponent, put the reciprocal in front. Okay, so what this is telling us is that when it comes to 1 over x, the integral is something completely different. It's the log. It's different from the other ones, right? However, when there's the log, we will usually have an absolute value there. But let me try to explain why that is so. So to understand what's happening with that, try to do ln of negative x line.
Would that be negative 1 over x?
So we apply the chain rule, right? So it's 1 over this thing, negative x. Treating negative x like a single letter, right? So ln of something that comes down here. But you don't stop there. You have to use the chain rule. What does the chain rule say? Multiply by negative x derivative, right? You do that, which is negative 1 over x times negative 1, which gives you 1 over x. Okay, tell me what the corresponding integral statement is. Integral of
1 over x
1 over x
dx
dx is
equal to ln negative x
ln of negative x
plus c.
plus c. Oh wait, that's strange, don't you think? Here it says the integral is ln of x. Here it says the integral is ln of negative x. Which one is right?
Is it possible that there's many solutions?
That's another thing. So one thing that I forgot to say is that if you have two different antiderivatives of a single function, you can show that they differ only by a constant. I don't want to do it right now. But the problem is these two functions are not differing by a constant, unless you allow complex numbers. But here we don't use complex numbers, so these are different functions. So at first this looks really puzzling. But then if you draw the graph and start to think about it, then it starts to make a little bit more sense. So remember, what's the graph of log of x? The graph of log of x, it has an x-intercept at 1. It goes like this. That's ln of x.
Oh.
If you have a minus in front of x, ln of negative x, do you know what the graph is? If you replace x by negative x, what happens to the graph?
Would it just be
It
mirrored
flips
along the
over, which way?
y-axis?
It
Just
flips
mirror
over
along
the
the
y-axis.
y-axis, right?
Yeah. So this is the graph. And this is ln of negative x. Okay. Now from the graph, you immediately see that these two functions are not only just different, they have completely different domains, right? What's the domain of ln of x? Yeah, x has to be positive, right? What's the domain of ln of negative x? X has to be negative, right? That's because since log can only evaluate positive numbers, for negative x to be positive, you need the x itself to be negative. So domain of this function is actually negative. That's why you only see the graph on the left side, whereas this graph is on the right side. Okay, now to understand what's happening, let's also draw the graph of 1 over x. They appear in both equations, right? So let's draw the graph of 1 over x. Here's the graph of 1 over x, here's the graph of 1 of x. You probably know that 1 over x has a vertical asymptote as the y-axis and horizontal asymptote as the x-axis. So it's this. It actually gives you two different curves. It's a hyperbola, geometrically. And if you look at the statements that we have, which is saying that the slope of this function is 1 over x, and you look at the graph, it does make sense because what's the slope here? It's a very high, it's a steep line, right? So the slope is very big. And of course, the value of this red graph is big. As you go further to the right, you get a slope that is very shallow, right? It's closer to a horizontal, it gets closer and closer to a horizontal line. And sure enough, this red curve here is getting closer and closer to 0. So you're convinced that in fact, the antiderivative of this red one is this white one, or the derivative of white one is this red graph. Is that good? Can you make sense out of the two? I mean, if you didn't pay attention to the left side and just looked at these two graphs, and you ask the question, which one is the derivative of the other? And you'll be able to say, well, the red one doesn't have the derivative of this one, because here you have a negative slope and this is positive. That doesn't make sense. But if you do the opposite way, to think whether the white curve has the derivative as the red graph, it does make sense. Yes?
So how come you have to use the chain rule for the ln negative x though, and then ln x is 60?
Okay, so the question was, how come I'm using the chain rule to differentiate this one, whereas I'm not using the chain rule for this one? If you insist, I can use the chain rule for this one as well. So since x is nested inside, right? I apply this, and what does the chain rule say? You have to do that, right? What is the derivative of x? 1. So you get just 1 over x. But usually you don't have to do that because it's just x. We use the chain rule if there's something complicated in there. Okay. So back to this, we convinced ourselves that the right side is indeed correct. Now let's look at the left side. Look at the slope here. It's a very steep slope, but in the negative direction because it's decreasing, right? So it's a big negative number. And indeed, the red line, the red curve, becomes more negative as you get closer to 0, right? And as you go to the left, it becomes closer to a horizontal line, so the slope gets closer and closer to 0, and sure enough, this does get closer and closer to 0.
A question.
Yes?
Are those the two red lines? That's 1 over x, right? They're both 1
Yeah,
over
yeah.
x.
So the two curves, this is one function.
Oh, okay.
Yeah, this is one function. Y goes to 1 over x creates both functions. Okay. Whereas y equals to ln of x only creates this right side, and y equals to ln of negative x only creates the left side. But I'm saying separately, when x is positive, the derivative of log of x is this. When x is negative, the derivative of log of negative x is this. And both are correct. Okay? All right, so once you have the graph, you kind of gain a better insight into what's happening here. The problem here is that you really want to say, if there's a single function that you can call, if there's a single function whose graph is both white lines, white curves, then we can say that whatever that function is, the derivative of that function is this red one. Do you agree? You get that, right? But because these are only defined for positive and this negative respectively, they satisfy these equations. So this one is only true for the left side, that one is only true for the right side. So here's the question. Is there a single function that actually creates both curves? And amazingly there is. And the answer is that it is the ln of absolute value of x. So here's what I claim. Claim ln of absolute value of x actually becomes ln of positive x if x is positive, and ln of negative x if x is negative. Now let's see why that is so. Well, the reasoning is simple. Oh, and by the way, if you accept that, then you see that ln of absolute value of x will create both graphs at once, right? And the outcome of this is that if this is true, the upshot of this thing here is that if you have ln of absolute value of x, then the derivative of this would be 1 over x plus c. Just 1 over x, right? So it contains both results at once, and let's talk about what happens afterwards later. All right, so we really want that claim to be true, and how do you argue for it? Well, here's the simple reason. Absolute value of x is what? It's same as x if it's positive. Do you agree? If it's positive, then it gives you x, right? On the other hand, when x is negative, even if it's 0, it's the same thing. If x is negative, absolute value of x gives you negative x. That's the definition of absolute value of x. And now all you have to do is just apply ln to that definition, and you get this. So that's the proof. Okay. How do you like this definition? Have you seen this definition of the absolute value? How many of you have seen this before?
Solving.
3 people? Okay. Now, when you see this, I'm asking to those who have never seen this before. If you see, since you saw this for the first time, do you think this is really the definition? Or does it look puzzling? Huh? Bit puzzling?
If you put anything negative in the absolute value, what is positive?
Okay. So that's actually a very good remark. So, if you saw this definition for the first time, there is a puzzling aspect of this formula, because all your life you're told that absolute values take away the negative sign, right? But here in the definition, it seems to say that it's creating a negative sign. And it doesn't agree well with your own intuition that if you put a negative number, you should be taking away the negative sign. Okay? However, I still claim that this is the correct one. Why? Why does this agree with what you just said? Yes?
Because if you negate a negative, it becomes positive.
That is the exactly correct answer. So the reason that this is the correct definition for the absolute value is that if x is negative, then negating a negative number will make it positive. So here's another way to explain it. Don't be fooled by the looks. Negative x looks like a negative number, right? But it's not. Why? Because x itself is a negative number. So even though it looks like a negative, it's actually a positive number. Does that make sense?
Yeah, but what if
Can
plug
you
in
see
a-
this negative x and say, oh, since x is negative, this is actually a positive number? Does that make sense?
Okay. But you're saying if only if x is negative, what if it's
If
positive?
x is negative, then it's going to be, this will be a positive number.
So if it's positive.
If x is positive, this will be the positive number.
Oh, okay.
Yeah, right?
Yeah, that's what I'm saying.
Okay. So are we clear on that? Yes?
Can you show us the numbers?
Oh, yeah. Okay, what does this do according to this? It's negative, right? So you have to apply this.
So
So it's negative of negative 1. Because x is negative 1, so you have to replace x by negative 1, right?
Okay.
So it's negative of negative 1, so it becomes positive 1.
Okay.
So what if it's -1 on top? It'd just be -1?
No, you can't plug in negative 1 here because x is not positive.
Oh, yeah, that's right.
Yeah. So if you have absolute value of 3, then it's this case, so you have to follow this one, which is just,
So where you have x and negative x, those are just conditions.
these are conditions.
Yeah.
These are conditions, and according to which condition it follows, you have to use different definitions.
Okay. Okay.
Now, if you're still confused, then here's another way to think about it. Just draw the graph. When x is positive, y equals to x is this graph, right? When x is negative, y equals to negative x is what graph is it? It's this one. Isn't that the graph that you knew all along? That's the graph of the absolute value. So this does correctly describe the function absolute value of x. Yes?
So like, how is this beneficial?
Okay. Well, how is it beneficial was the question. Well, by writing that, we were able to be convinced that this is true. Right? Okay? By accepting this, we were able to say that this is true. Okay, so what is the final conclusion here? The final conclusion is that from now on, when you integrate 1 over x dx, what do you write? If you switch the statement, switch the derivative statement into an integral statement, what do you get? ln of what?
Absolute value.
Absolute value of x plus c. So that's what we're going to do every time. So when you have a statement with logarithms, you should really have the absolute value because of this graph. Any more questions? Okay, I want to throw something out there which is not really needed. You don't have to know this, but it's actually a pretty interesting observation. This is in every calculus textbook, but this is still slightly wrong. It's slightly wrong. Okay? And the reason is, you take these white curves and you can add anything to it and the derivative wouldn't change. So for example, I let it stay as ln x. But let's say I add ln of negative x, I add like 3 to ln of x, so the new graph is this one. Okay? Now if you differentiate this, you still get the red curve. Don't you agree? Yeah, because the constants, whatever you put there, that gives you 0, right? So whether you shift it up by 3 or anything, it doesn't matter. So what that actually says is that the really, really correct answer is that the antiderivative of this has to be ln of x plus c1 if x is positive, right? And ln of negative x plus c2 if x is negative. So that's the really correct answer. Where the c1, huh?
Would there be a greater than or less than or equal to sign?
Oh, so here I don't want to put the equal sign because when you plug in 0 into log, it's not defined.
Well, what if x was 0?
Oh, it's not defined.
It
This
wouldn't be zero?
function itself is not defined.
Okay.
Actually, that's the reason why you can have these two different c1s and c2. If you have a continuous function and you're looking for a continuous antiderivative, which you have to, because by definition, antiderivatives are differentiable. Any differentiable function is continuous. Yeah. Then in that case, you can only have a single constant. But if you have a function that's discontinuous, then the entire derivative can have discontinuity at that point, and you can have two different c1s and c2. Yes?
So
So technically it's discontinuous instead of continuous.
This one has to be discontinuous because the original function is discontinuous. Yeah, but that's like not. Yeah, nobody talks about this because for practical purposes, this is never used. When you have to find the antiderivative of this, you either always confine yourself to the right side or the left side, never both. Actually, it doesn't make any sense if you do that. So that's why this is enough. Yes.
So if you're trying to find the antiderivative of anything, you would put absolute value of that.
So if you have an antiderivative and your result has log,
You put that.
you put the absolute value. Well, there are some exceptions. Like if you have, say, well, we haven't learned how to integrate this, but you'll see that if you integrate this, it's ln of x squared plus 1 plus c. Here you don't need the absolute value because x squared plus 1 is always positive, right? So there are some exceptions like this, but anytime you see that if this can fall to negative, then you have to account for it by putting in the absolute value.